Hello class, for this video we are going to go through another review of chapter 3, this time on the topic of linear independence. Let us separate away the case when we have two functions and the case when we have three or more functions, because the two function case is a lot easier. So when we have two functions, the question that we are asking is simply, is their ratio constant or not? If fx over gx is constant, we say that the functions fx and gx are linearly dependent. If fx over gx is not constant, then we say that fx and gx are linearly independent. One way to remember this is that if fx over gx is constant, this means that fx is a constant multiple of gx, and this implies a very close relationship. So linear dependence simply means that the functions are very similar to each other. That's more or less what it means. So if the ratio is a constant, it means one's a multiple of another, and that is a very strong relationship, and so they depend on each other. For three functions, there are actually two definitions of linear independence that are useful. The first is the Wronskian definition, and this is typically the definition you want to use for actually calculating linear independence. It's easier to use, I think. So if you have three functions, fx, gx, hx, you can write down a 3x3 matrix by taking the first and second derivatives like so. If the determinant is 0, you have linear dependence, and if the determinant is non-zero, you have linear independence. Those of you who have taken linear algebra will know that the determinant will be 0 when the columns of the matrix are similar to each other, and that is why the determinant being 0 implies linear dependence. So remember, linear dependence has the implication that the functions are very similar to each other. The second definition is this combination definition, or linear combination definition. A linear combination of three functions is simply this, that you multiply them each by constants like k1f, k2g plus k3h and add them together. If this combination is equal to 0 only when k1, k2 and k3 are all 0, then you have linear independence. But if it is possible that k1f plus k2g plus k3h equals to 0, even for k1, k2 or k3 non-zero, then you have linear dependence. The reason that this strange condition is related to linear dependence is that if you have a combination equaling to 0, then this implies a relationship between the three functions. And remember, linear dependence means that the functions have a close relationship. They depend on each other. Whereas if you have to force them to equal to 0, then they aren't very friendly to begin with, so they are very independent from each other. Let us discuss briefly now why linear independence is so important. So let's think about how we solve a third-order linear homogeneous equation. We find three solutions, f, g, and h, and then we use the principle of superposition to write down a solution as c1f plus c2g plus c3h, and this is our candidate for the general solution of the differential equation. However, if f, g, and h are linearly dependent, then we know that k1f plus k2g plus k3h for some k1, k2, k3 that are not all 0, so either k1 is not 0, k2 is not 0, or k3 is not 0. So let us consider the case when k1 is non-zero. Then we can solve for f like so, dividing both sides of the equation by k1 to get fx equals minus k2 over k1 gx minus k3 over k1 hx. Notice that this is impossible if k1 was 0. And then we can substitute this value of fx into our supposed general solution, and we obtain this expression c1 minus k2 over k1 gx minus k3 over k1 hx plus c2 gx plus c3 hx. And we can rewrite it in a form separating out the gx and the hx functions. And what we get is that we can rewrite the constants as y equals agx plus bhx. Now, this is problematic because, as you may recall, this was supposedly a general solution for a third-order differential equation. And third-order differential equations typically have three constants in their general solution. But we have somehow rewritten this general solution to have two constants. And that is why linear dependence is bad, because it gave us a fake general solution. If f, g, and h were linearly independent instead, it would have not been possible to reduce the constants in this way. And that's why we care about the linear independence of our solutions.